Imagine a brilliant scientist born on a world entirely blanketed by thick storms. She has never seen the stars. She has no idea her planet is spinning rapidly through space. When she measures the motion of pendulums or watches massive weather systems mysteriously curve across the sky, the physics don't add up. To make her math work, she invents a complex system of invisible dark forces pushing and pulling on her environment. For the last 100 years, human cosmologists have been sitting on our own cloudy planet, observing phenomena that break our standard models, and building identical mathematical patches to explain them. We look at spiral galaxies and see them rotating far too fast at their outer edges. We see fragile spiral arms persisting for billions of years instead of winding themselves tightly into a blur. We even observe a strange statistical bias where galaxies across the cosmos seem to prefer spinning in a specific direction. To balance the cosmic ledger, astrophysicists hypothesized a massive, invisible substance called dark matter. It supposedly makes up the vast majority of our universe. But after decades of searching and billions of dollars spent on highly sensitive underground detectors, no one has ever found a single dark matter particle. Theoretical physicist Boris Krieger has published a radically different explanation. He argues that the particle hunt is failing because the missing mass isn't a particle at all. We are simply measuring the universe from a rotating reference frame. If the fabric of space itself is spinning, the need for a mysterious dark sector evaporates. The phantom mass holding galaxies together is replaced entirely by the physical geometry of space. Standard cosmology assumes a flat, static grid. Krieger's model replaces this with a compact RP3 manifold containing two perpendicular planes of rotation. These planes lock into double counter-rotation, spinning in perfectly opposite directions. Their overall angular momentum cancels to zero, but inside, space keeps moving. General relativity dictates that a massive, rotating object literally twists the fabric of spacetime around it. This is a proven mechanical effect called frame dragging, confirmed by NASA's Gravity Probe B mission. Krieger applies this principle to the entire cosmos. If the universal manifold itself is rotating, then space is constantly dragging all matter along with it. This graph of galactic rotation shows the problem and the solution. The bottom curve shows standard gravity, predicting stars slowing down. The middle curve is flat observational data, currently attributed to dark matter. The top curve shows Krieger's frame dragging effect. Rotating space scales up to perfectly match the flat data. This global frame dragging provides the exact mechanical tension required to hold a galaxy together, eliminating the need to wrap every star system in a massive invisible halo. Embracing this math requires throwing out our default mental model of what a galaxy actually is. We are taught to think of them as giant solar systems, where a heavy central bulge neatly dictates the stable orbits of everything around it. That classical model has a massive flaw called the winding problem. The inner stars of a galaxy orbit faster than the outer stars. Under standard orbital physics, those beautiful, sweeping spiral arms should shear apart and blur into a featureless disk in about 500 million years. Krieger suggests galaxies are actually space-time cyclones. They function remarkably like weather vortices forming within a rotating fluid environment. Think of Jupiter's Great Red Spot. It has persisted for centuries, not because of its own internal gravity, but because it is actively maintained by the rapid rotation of the planet itself. In the same way, global frame dragging acts as an external restoring force. As differential rotation tries to tear the galactic arms apart, the rotating space they sit in drags them back into place. This cyclone mechanism also solves the cosmic handedness anomaly. The rotating geometry of space contains twisted fibers, known as Hopf chirality. As gas and dust fall inward to form new galaxies, these twisting spatial currents mechanically deflect the matter, creating a measurable bias in which direction the resulting galaxy will spin. A galaxy's intricate shape and specific rotation are not random, local gravitational accidents. They are the direct physical imprints of a rotating cosmos. Krieger's rotating universe is a strict, testable mathematical model. It makes highly specific, falsifiable predictions that stand in direct opposition to standard dark matter theory. As we map more of the sky, the preferred spin direction of all spiral galaxies should mathematically converge on a single calculable coordinate axis. Additionally, the cosmic microwave background should display a precise asymmetry in its temperature fluctuations, a parity anomaly dictated by the folded shape of the rotating space. We don't have to wait decades to find out if this is true. Next-generation observatories and deep space mapping projects are pulling down the exact datasets required to verify these topological signatures right now. Cosmology is facing two very different paths. We can continue an increasingly expensive century-long hunt for invisible particles that refuse to interact with our detectors, or we can look closely at the geometric reality of the space those detectors occupy. The dark sector driving our modern models might simply be an illusion. It is the exact mathematical error you would make if you were standing on a cosmic merry-go-round, completely convinced that the ground beneath your feet was perfectly still.